So last time was our second lecture in pointers, and we discussed more advanced topics in pointer other than just defining them, like doing some arithmetic operations in pointers and how to deal with them in functions, etc. Today we are going to continue this. We will finish the last lecture first with this topic, which is dynamic memory allocation, one of the most important applications of using pointers in C especially. Did the sound like too loud? It's like, is there a noise? Are you okay with that? In the back? Good? Okay, so dynamic memory allocation. You remember, so far, the way we allocated space in memory was using what? How did we allocate space in memory? Like big chunks, not just variables. Because defining a variable, you already allocate a space in memory, right? But bigger than one variable size, how do we allocate space in memory so far? Yeah, arrays, right? Using arrays. We said arrays are contiguous storage in memory that once you define it, you allocate the full space. We said arrays has one big problem, is that you have to define this size from the beginning, right? So once you define an array, the program or the hardware at the end will reserve for you this storage in memory. Whether you use it or not, it doesn't matter, right? They will be occupied for you. And there are some applications that you don't know this space before, right? You don't know how much memory you will need. You cannot resize arrays, at least in all versions of C. And even in the new versions, they do this indirectly. So it's an inefficient way of defining a dynamic memory. We can call this static memory allocation, because you statically allocate a specific say number of entries or size of storage in the memory. Right? Another limitation for arrays, or if you can think of arrays as a storage in memory, is all the variables or all the things that you are going to store in this memory has to be what? What is this condition of arrays? Same type. You cannot store int, character string, Boolean variables, different type of things on the same memory space. So think of this, think of arrays from this perspective. You allocate a specific storage in memory. It has to be fixed. And at the same time, you cannot use this area in memory or this contiguous storage except for the same type you defined your array, right? These are two big limitations of arrays. How to get across this? How to define a dynamic memory space for you and to store in it whatever you'd like to do, because memory is memory, it just stores zeros and bits. It shouldn't matter what type it is, right? How to do this? We do this in C and in most programming languages using what we call dynamic memory allocation through pointers, right? So there are multiple functions of doing this, but this is basically why dynamic memory allocation is important, and this is one of the biggest applications in pointers in C. Before going into this topic, this slide is discussing what we covered before. Is you have what we call automatic storage duration for your variables and even arrays, or memory allocations in general. We said once, if you have a local variable, for example, inside a function, it's a kind of a review to refresh your mind. If you have a local variable inside a function, what is the duration that this variable will stay in memory? What is the point that is going to be defined or allocated in memory when you enter this function, right? When it's going to be deallocated from memory when you exit the function. So if it's a local variable, the duration that this variable will stay in memory is within the block you defined it, whether it's a function or a for loop or if condition or whatever, right? On the other hand, if you want something to stay in memory for the complete duration of the application, you have to define it as what? Static, right? So if you define a variable as static, it gets defined, it gets allocated in memory at the beginning of the application, and it gets deallocated at the end of the application or the program, no matter whether you are using it or not. But defining it as a static doesn't mean you can use it anywhere in the program. So static and global has two completely different meanings. Static is with the duration of like how much time or what is the duration that this variable will stay in memory. It doesn't imply anything about its usage in the program. If you have a local variable, it can be static, so it resides in memory, but you cannot use it outside the block you defined it. And we had an example of that, right? This is a static variable. On the other hand, if you want a variable to use everywhere in your program, then maybe you need to define it as global variable, right? So this is what we discussed, maybe like in a brief or nutshell, about memory allocation and the time or the duration that a variable stays in memory, right? As you can see, this is like very, very limited thing. So basically based on the type, you have limited rules. You have to obey these rules, good? If you want to get across this, you need to use dynamic memory allocation, good? So you can do dynamic memory allocation in C using two main functions, malloc and we call it calloc. So malloc is the mostly used one, and this is referring to memory allocation, malloc, right? And calloc is very similar, but the difference is basically it refers to contiguous allocation, and as we will see, it has little differences between malloc and calloc. Reallocation or realloc is if you already define the space and you want to change its size, for example, right? So what does these functions do? They reserve for you also a contiguous portion in memory, and they return to you a pointer to the start address of this memory location. Somehow very similar to how array works, right? Once you define an array, the array name can be used as the start address of the array. So if you think of an array as a contiguous memory, then the start address is the address for the first element, very similar to here, right? But using malloc, let's focus on malloc and everything else is similar. If you use malloc, first of all, you can resize the memory that you defined. The second thing is you are not tied to a specific type. You just define a memory space for you. You reserve it if it exists. And then it returns a pointer to the first address. You can store there whatever you'd like to do. Good? So it's called dynamic memory allocation. So one last thing is, and this is the cost of having a fine-grained control in C. You define your memory yourself. So you have to take care of, you release this memory once you are done with it. Otherwise, your program will run out of memory, right? And one of the biggest mistakes, like this is something that is very common in C, especially for someone who is not familiar with C and is familiar with other languages. In C, you handle the memory yourself, right? So you allocate a chunk of memory, you deal with it, and then at the end you have to free it. People forget to free the memory. And then they exit the program, like not exit the program, like they exit the function. For example, they're using this memory and go to another function. They try to do another malloc or do another array definition or something that uses memory, but the program crashes. The reason is you don't have enough space in memory. Why? Because you allocated big chunk, you used it, but you forgot to free it. So you have to use the free function once you are done with your memory allocation. So the steps to do this is you start with allocating a memory that you would like to use. Try to be constraining for yourself. You can define whatever you'd like to do, but use only the memory that you need. You perform your operations, and once you are done, you free. Good? Okay, so let's see some examples of how to do this. But before going to malloc, I told you that malloc is reserving to you a certain storage in memory or a certain portion in memory and returns a pointer to the first address. But what we covered so far is a pointer has to be to a specific type. Right? We discovered like int pointer, character pointer, double pointer. So a pointer is an address that is pointing to another variable, and this variable has a specific type, right? But now, I told you that the second limitation of an array is you have all the memory that is allocated to an array has to be of the same type. This does not exist in dynamic memory allocation. But how to do this? The way they do this is the returned pointer from the function, which is malloc, is of type void. It basically is not constraining you with any type. So we have in C what we call a pointer to a void. So it's not pointing to a specific type so far. You can later reallocate it to a certain type. And this is the good thing. This is the trick, right? But because this is a void pointer, it's not pointing to a specific type, we cannot do math operations on in this pointer, right? Why we cannot do that? Because if you remember from Monday's lecture, to do math operation on pointers, you use the size of the data type that the pointer is pointing to in your math calculation. So we had an example of if you have a pointer to an integer and then let's say to an array of integers, you have, like the pointer is pointing to A1. If you want to go to A2, you just say B plus 1, where B is the pointer. Why does this work? Because the compiler is going to take the 1, multiply this by the size of the integer, which is 4 bytes, and then jump to the second element, right? So the math, if you look into the early slides of this lecture, there is a math equation where the size of the type is included in the pointer arithmetic, right? But if you have a void pointer, you don't have a specific type, and in this case, you cannot use this equation, right? You don't know what is the size of the memory that you are pointing to. Is it 4 bytes because it's an integer? Is it a character, so it's just 1 byte, right? This is why you cannot do a math operation on a void pointer, right? Later, if you reallocate a pointer of int and then point to the same address, then you can use the other pointer, right? And for the same reason, you cannot do dereferencing with that pointer because it has no value. It's not pointing to anywhere, right? It's pointing to a specific address, but not of a specific type, right? So this is the usage of malloc. This is the prototype. It returns a void pointer, and it takes an n. Size c is inherently an integer value, but a specific type in C. I'm going to explain this right now, but this is referring to how much memory you want to allocate for yourself, right? So what happens is it allocates consecutive bytes of memory. It returns a pointer which is void 1 that is pointing to the first type. What if I don't have enough space in memory? Because I keep telling you that this is dynamic memory allocation. You can do this on the fly. But assume I'm trying to allocate 4 gigabytes and I don't have that much space in memory right now. What will happen is malloc is going to return to you a null pointer. Good. Later in your program, you have to use this null pointer as an indication that your memory is not allocated. Otherwise, if you don't take this into account and you try to use the memory, you will have segmentation fault. You are referring to a memory location that does not exist. Good. So what you need to do is, if malloc is returning a null pointer, you have to do a check in your program before using the memory that you allocated for yourself. Good. We'll have some examples now. Before going some examples in malloc is exactly the same thing, except that it takes 2 things. Because the way malloc is allocating memory, malloc is a contiguous place in memory that is not of any structure, right? Malloc, on the other hand, it allocates a memory space as if it's for an array, right? This array has m objects, and each of these m objects has n bytes. So as if you are defining an array, I can use my pen here. And then you have in this array m objects. Each of them has the width of n. This is how to interpret calloc, right? On the other hand, malloc is just 1 byte width. This is why you don't need the other variable here. And then it has here, in order to make it the same syntax, let's call this m, and this has m objects, right? So for malloc, you have m objects, each one of them, or m entries, each one of them is just 1 byte by default. So it's a contiguous place in memory. But calloc, the way it defines it, you have m objects, but also you have another number here, which is n, which is telling you what is the width of each entry here. Good? So think of this as if you have m integer objects, and each one of them is 4 bytes, right? Because integers are 4 bytes. Right? So there are very little differences between malloc and calloc. One of the differences is calloc, because it somehow inherently tries to simulate array reservation in memory. It do initialize all the memory locations for you, right? So if you allocate a memory space using malloc, it does not get initialized. Whatever garbage in the memory, if you read it without writing into it, you are going to read it. But memory allocation that is done using calloc, any memory address within this portion is initialized to 0. This is good because it does the initialization for you, but also it has a disadvantage that calloc runs slower than malloc because memory allocation takes time. One of the things that consume time in C is memory allocation. So if you do memory allocation using calloc, you have to take into account that if it's a large chunk of memory, as if you are doing writes to all these memory locations. So it takes some time to get it allocated. So if you don't need the initialization, actually it's not important to use calloc. And most of the big programs are actually using malloc, not calloc. Right? But other than this, there is no big difference between both. Yeah, for both you have to free it.
Like, what if it can't make the request? Does it still fill up some memory? And then it realizes it can't make the request?
You cannot make a request means you cannot allocate this. So I don't get your question.
So, for example, there's like a certain amount of memory.
Yeah.
And when does it realize it can't make a request? At the end or before it starts?
I see what you mean. That's a good question. So your question is, while I'm doing the allocation, when I realize that I don't have enough space, is that when, before I start, or I keep allocating until I hit something, right? Yeah, this depends on the hardware, because this function is using some hardware support. Some memory structures, which are the common for high performance ones, keep a list of how much empty storage you have in your memory right now, such that if malloc or calloc are used, and by the way, both are dealing with this problem the same way, so there is no difference between them. Initialization have no effect here, right? Some of the hardware will tell you at the beginning, you already have so much space, so you compare with this space, and then if it's larger, then you know from the beginning you don't have an issue, right? And then you can just allocate. But even in this case, you are not sure that you are running alone, because you can have hundreds of programs running, all of them are trying to do malloc or calloc on the same time, right? So even with this support, you still can have the case that you start allocating and you hit a point that you don't have space, and then you free anything. We'll have one example right now that you need to handle freeing the space yourself in some cases. But in most cases, what will happen is either malloc or calloc, if they already allocated a space, and then reach a point that there is no much space, and this space that is allocated is less than the size that you asked it for, they by default free everything and then give you a null pointer. So they do the free for you, right? Is there any other question? Good. So as I said, to deallocate the memory, use the free. Free is taking an input, a void pointer. What is this pointer? What is the input parameter to this free? Malloc had no input parameter. Why free has an input parameter? Yeah. Yeah, which is the same pointer that is malloc returned, right? So you have to give free the start address that the memory has to start free, right? So this pointer is like the address of the house or the address of everything that you allocated for yourself. Why you need to free, right? And then it deallocates the memory starting from this. And if you try to free something that you didn't allocate using malloc or calloc, it will give you an error, right? And then if free didn't do the free for you, it will return a null pointer. So again, you have to, if you want, you can double check whether the free operation is done successfully or not, right? Okay. As I said, you have to free the memory that you no longer need, otherwise your program will run out of memory, right? And it will be inefficient. The allocation, this is not required from you, but this is for your information. Assume I already allocated something dynamically using malloc. Allocated, I don't know, like 1 megabyte. Later I found that my program needs more memory. And I need this memory also to be the same chunk as the 1 megabyte, but I want to increase 1 megabyte to be 2 megabytes. Then you can use reallocation, realloc. The way realloc works internally is it's not necessarily going to reserve the 1 megabyte that is directly sequential to the first megabyte, because you are not sure this will be free in the memory at this time, right? So if it's free, it's going to be allocated, but if not, then it's going to be allocated somewhere else, and then point to this place. So as if virtually, they are one chunk, but physically in hardware, they don't need to be contiguous, right? So the problem with reallocation is you are not sure that the new space is going to be contiguous or the same block that like the malloc did. By the way, why I care whether this is contiguous space in memory or not? I already mentioned this before, but can someone say a hint for a bonus mark? I keep saying malloc or calloc or array gives you a contiguous area in memory, like storage in memory. Why this is important? Some new face from the back. Why it matters? Yeah.
Because if you want the user to, let's say, input 9 into an array, and you're going to input, then you can use this, you can use it on your
Even if they are not contiguous in memory, you can still use them as if they are one entity. So there is a difference between whether they are physically contiguous or not, right? So what you are saying is, if they are contiguous in memory, I can use this as an array and then increase the index, for example, right? Is that what you are saying, right? So what I'm saying is, there are some data structures, we didn't cover this yet, but even if you get allocated entries that are not contiguous in memory, you can still use this index pointing to it. But it's not related to programming or usability of programming. Yeah? Specify the data type. No, here in dynamic memory allocation, you don't have to specify a data type. Some other new case? Yeah? Yes. Why this is the case? Why they are faster to access? They are beside each other, and then they can get allocated to the cache near the processor faster, right? So I told you before that the way your laptop is structured is you have off-chip memory, which was what we call DRAM, and then you have on-chip. On-chip means it's close to the processor, faster cache, right? And accessing caches are much faster than off-chip memory. Like caches are like 1 to 10 cycles. Off-chip memory is like hundreds to 200 cycles. If something is contiguous in memory and you access it on the off-chip, everything is brought to the cache at once, and then you can use like faster access to it. So caching mechanism in hardware is highly reliant on what we call locality concept, and locality is based on whether this memory space is contiguous or not. So if you are accessing something that is contiguous in memory, it's much faster than something that is not contiguous. Later, you will see this in data structure course. The access time of an array, access time means how much time it takes to access an element in an array. It's called O1, which means it's constant time. Whether you access first element, last element, mid element, doesn't really matter. They take a constant time. In other data structures, which are efficient in other cases, but their access time is not constant time. Why? Because they are not contiguous in memory. Array is contiguous in memory. Okay. Is there any question? Okay, so let's use dynamic memory allocation in defining a variable length array. Okay. Assume I have a main function, and then I ask a user to input to me the size of the array. It's the first time we do that. And then I read the size of the array using scanf. By the way, I need to check whether this size is positive or not, because if it's less than 0, I cannot allocate an array or any memory location of negative size, right? So this is a check that we do here. It's a sanity check to make sure that the user is not doing something wrong. Right? And then I use malloc here. People are here. I use malloc here to allocate the size of the array that I want. Assume that this is a float array. The way I do this is I multiply n by the size of float. What is that? What I'm doing here? If you have an array of type float and it has 10 elements, and we assume that the float size is 8 bytes. Assume this for now. It's machine dependent, but assume it's 8 bytes. That means this array that has 10 elements, how many bytes it needs in memory? 10 multiplied by 8. You need 80 bytes, right? This is exactly what we do here. We have an array of size n, but I know each element or each entry in this array has a size of 8 bytes. This is what size of function is doing. Size of is a function in C that takes as an input multiple things, multiple different things. It's like a magic function. It can take a data type, as you have here, size of float. We used this before, right, to check what is the size of int in our machine. it can take an array, it can take a variable, and it returns to you what is the size or the memory number of memory bytes that are allocated to this type. So for example, size of float, it can be 4 bytes or 8 bytes, right? And then it multiply this by the number of entries. This is how much chunk in memory I need to reserve for that array, right? And it's done dynamically. Then malloc, I'm taking its output to a null array, right? Here I'm defining a float pointer, it's null, and then I'm reading the thing here. Why it's float? Because I know for now this is a limited example because the whole chunk is of the same type, float, right? We can say malloc can actually store anything. It's not necessarily all elements are floats, but for now we are using it as floats. And then I'm returning a pointer to a float. Good? Then let's say I want to loop through this array or dynamically allocated memory and then print it back, right? Or read the values and then put it in the array and then print it back. So after reading the size of the array, I ask the user to input the array elements. I do a scan. Now here is a trick. We had this before, right? Last lecture, we said to access an element in an array, there are four different ways. One of them is to use the pointer that is pointing to the first address plus the index of this element. So b plus I is effective too, as if you are saying AI of an array, right? Had this before. Good. And then here I'm printing back all the elements of the array, right? Saying like b of 1 equals this, b of 2 equals this, etc., until I finish n. Is there any question here? Good? Okay. At the end, before I finish my program, I have free b. This is how you do the free. b is the address, the pointer that is returned from the malloc function. You use the same pointer to free the whole chunk of memory. Good? As you can see, free doesn't need a size, right? Malloc takes a size, but free links that you already allocated this portion of memory, b was pointing into it, and then if you pass back b into this memory, it knows already the size. Right? This is why you need to pass exactly the same pointer that you got back from malloc. Any question? Yeah. Yeah, what is this, right? There was a slide that I left for you for reading, and it has this information. It was, I guess, 4 lectures before. It's basically telling you how many digits you print and what is the accuracy for this. Right? So go back to this slide and you'll find the answer. Any other question? Good. So now we have another example. Let's say we want to write a function. Honestly, originally, my original plan was to add this example as a quiz, right? Because it's a long time since we had a quiz and it's not fun, right? But because pointers took too much time than what I have expected, and because you ask questions, but that's good, I like that. So I'm thinking in a different way of how to handle the missed quiz that we missed so far. But I'm going to explain this example for you. It's not a quiz, right? So if you have any question also in this example, let me know. And think of if now I give you this as a quiz, whether you will be able to handle it or not, right? Right? So think of, because if you don't have any question, that means you either completely lost, which is too bad, or you guys know everything, which means you can solve this quiz, right? Okay. So what we want to do is we want to write a function that adds 2 n-dimensional vectors. Vector is like a different terminology than an array. There are slight differences. Because vector is actually a data type in a C library that uses dynamic memory allocation. It's not like an array. It can be a variable size array. But for now, let's say, this is why I don't call this n-dimensional arrays. Because people usually use array word for the fixed size. If you have a dynamically allocated array, it's better to call it vector. This is the language that programmers are using. Okay? So to add 2 n-dimensional vectors, each vector is stored in an n-size array. Then the array names corresponding to the vectors to be added are passed to the function as arguments. So I want to write a function that takes as an input two vectors and adds them. Seems pretty easy, right? Except that n now is variable, right? This is the difference between whether you know the static size of the array or not. You have different options, right? I can, on the main or the caller, I can create an array that will store the result and then pass to this function a third parameter, right? As an array that holds the result of the addition. And because arrays are passed by reference by default, then if the called function or the add function is going to modify this array, it's going to reflect in the caller, right? Or now, given we already know dynamically allocated memory, I can write a function that stores the sum in a vector or a place in memory and return a pointer to this vector, right? I told you before you cannot return an array from a function, right? But you can return a pointer from a function, which can be a pointer to an array, and this is the trick, right? So this is our main. We define, we initialize the vectors. You can get the vectors using user input, whatever, but now we have them as initialized. And then you define an integer pointer, you initialize it to null, and then we write our functions like this. Takes vector 1, vector 2, and 4, which is the size of these two arrays. How would I write this function? Right? This is the thing. So one way of writing this, say these are two arrays. I take these by reference, which is by default. I take n, which is the size. I define an n sum of n. Can I do this? You can do this in later C versions, as we said before. You cannot do this in C89. You cannot define an array size of a variable, right? But you can do this in C99, and we said this is not allowed in this course, but let's go forward with that. What I'm saying is, this is actually not efficient. Why it's not efficient? Yeah? But you have to create a third array anyway, right? How would I add the two vectors? You are not allowed to change the two vectors, right? You have to create another storage anyway. And its size is equal to the size of the arrays, right? Do I have to take n as an input? Do I need even to define this n thing, which is limiting me? Now, given we know how to dynamically allocate like memory or arrays, I don't need even n. I can get the size of v1 and v2 and use this in my problem, right? So a different way of doing this is assume, but even before this, assume, this was assuming that this was allowed in C, right? Assume that in your X company, you are not allowed to use the later versions of C, like 99 or C++11 or something of that sort. Then you are not allowed to do this. Then this has to be constant, similar to what we covered before. So now, if I define n as a constant, what would be my size? Are you guys lost? So here is the thing. This is allowed in some versions of C. It's not efficient because you need to know n, you need to pass n, and then you use it. But there is also another limitation, which is some versions of C and compilers don't allow this. Don't allow to define an array of size variable. N is variable, right? What if I'm not allowed to do this? How to do it? You have to have the size of the array as a constant. Like let's say capital N or M or any name. That means you need to define it from the beginning. If I'm defining n capital from the beginning, what would be my size? Yeah. 4 if you know 4, but n is variable. You can read n from the user, right? We agree on that. So it has to be large enough to accommodate for the 4 for this example, but in general, it has to be large enough. Basically, the condition is n capital has to be larger than or equal to n small, right? If you don't know n, then the safe side is to allocate n capital as very large number. Right? This makes sense? Is 1000 enough? Is like 10,000 enough? Is like 1 million elements enough? You never know. But if you allocate it large enough, you lower the probability that it's going to fail, right? But, yeah. The problem is this is an array. You don't free an array yourself. It's going to be freed when you exit the program, right? So you don't have control on how to free it. Yeah. So if this is a local array within this function, it only gets allocated once you enter the function, deallocated once you go back. You don't have control on that. But you are in the right direction. Like if n is very large, I get allocate this large chunk of memory, like an array of size, like million elements, and I end up having an input of only 4 elements. That means I wasted 1 million minus 4 memory spaces for no reason, right? So this is why it's inefficient. Do you get that? It's inefficient because you have to define something static, you have to be conservative because you don't know what to expect, and you just allocate a very long chunk, a large chunk. Yeah, what's wrong with the small n is it's not allowed. There are 2 things wrong with it. First of all, it's not allowed in all versions of C. Like C89, it's not allowed. For NCC, it's not allowed in C. So the compiler will complain. Right? The other wrong thing, and this is why we needed this, the other wrong thing is also if you do the other thing in allowed versions, it's for sure more efficient than this solution, but you still have to pass n as an input parameter, and right? You still do some extra work that if you have dynamic memory allocation, you don't need. I can write this function completely without passing n, using the information we covered in this lecture, right? But you see why this is inefficient, right? Okay, so how to write it then? Then one way to write this, and by passing n, so as I said, you don't need to pass n because you can get this size from these arrays inside the function. But for now, let's focus on, if I pass n, how to get across the n capital large chunk. If I just have n, I only allocate whatever is needed. How this is different than the n capital thing? malloc, even in all versions of C, allows you to pass a variable number of entries, right? So this is valid in C89, and n doesn't have to be a constant. So you can pass n as a parameter, and then you only allocate whatever you need. In one run of the program, the user may enter n as 4. In another run, it can enter n as 4 million. And in both cases, the memory is allocated on the fly, right? So it's dynamically based on the user use case. And that's why it's efficient solution, right? Is there any question? Yeah. What is the difference between passing then or not passing it? Oh, what is the difference between this one and the first example? So there is no difference, right? Except that this is allowed in all versions of C, right? So I guess maybe the first answer of your first question was confusing, but the first one was a correct solution if it's allowed by the compiler. There are some cases that, but then maybe you guys ask yourself, okay, this is an old version of C, why I just use the new version anyway. It's not possible in all cases. In some projects, big projects, like in a specific use case, you have to use a specific version of C because of a certain support. For example, you work in a company that they had a project that was written 10 years ago, right? And then you have to do something with this project because another customer wants to enhance it. Then you are limited to this specific version of the program. You cannot change everything. It takes you like months and money, right? So in some cases, you are tied to a specific version and you have to deal with that version. Okay? Is there any question? Okay. So did you think if I gave you this as a quiz, you'd be able to do it? If not, then I guess maybe you guys need to start studying pointers because it's getting complex each lecture. Right? Okay, so more fun, arrays of pointers. We covered pointers to arrays, how to pass pointers to functions, how to return pointers from functions, dynamic memory allocation. Then pointer, I said this last lecture, at the end it holds some memory address, but at the end it's just a variable, right? You can define a pointer as a variable. So, and it's also stored in a specific place in memory, right? So what prevents you from defining arrays of type pointer, right? Each element would be a pointer. I can do this, right? And this is what we are covering in this lecture. So I can define an array of pointer of size 3. Can we imagine what is going on here? This will be an array that has 3 elements. And what is this telling us is each of these elements is an address to another place in memory, right? It's a pointer. Right? Make sense? Yeah.
So you would have 3 arrays?
No, not necessarily arrays. You can have 3 arrays, but you can have just 3 elements here. Right? This is a good question. What do you think? Based on the type we defined here, that means each of these pointers is a pointer to an end, right? So this has to be an end. You cannot have a string or like character or something here. Yeah, it will not work. You have to define this as a size of like a character or something, right? So arrays of pointers is telling you what is also the type that the pointer is pointing to. Good. So here, I don't know if you see from what I'm writing, but I'm initializing an array with 2 elements, 1 and 2. Another element. I guess maybe I should just use So here, I'm initializing 3 arrays. This is A, this is B, this is C. Then simply, because all of these are arrays of integers, I can make each pointer of this is pointing to this, as your colleague said, right? If I say BB0 is A, it's going to take the address of A. And then B, the address of B, C, the address of C. Right? So using arrays of pointers as if you are defining array of arrays, right? Because each entry in that array is an address to another array. Right? Does it seem fun? Okay, so if I want to refer to element AJ in array A, let's say A1 here. What you can say is, you know, A is pointed out by BB0, and then you can use another index here, J. This will, like BB01 will be 2, right? And the same thing for these things. So if you say A1, this is completely equivalent to BB01. In the last lecture, we also had this, which is dereferencing. We say BB0 is a pointer that is pointing here. You can add the index here and do dereferencing, right? This is a pointer math operation here. Because it's getting complex, please focus with me. What is going on here? BB0 is a pointer, right? It's a pointer to the first element in A. BB0 plus 1 is a math operation on a pointer. So adding a 1 to a pointer of type int is going to add 4 bytes, right? Which means you can use this as your index. And we had an example last lecture. So that means you are here, you increase 1, you go here. Again, this is still a pointer. What does the asterisk do? It does dereferencing, which means it's taking the value that this address is pointing to. So BB0 is here, add 1, go here, take the value, it's 2. Everything of this is the same. Right? Another example here. Good. So this is similar to what we said in last lecture. You cannot initialize a pointer. So you can have a pointer that is pointing to an array, but you cannot initialize a pointer with multiple elements, as if it's an array. So this is a syntax error. exactly similar to the previous lecture, because at the end BB3 is a pointer, and you cannot initialize a pointer like this. So one step further. But first, do you have any question here? Or do you have any question in general? Yeah. This, right? Okay, so let's take it step by step. A1 is 2, right? BB0 is this one, which is an address now. By doing BB0 equal A, is going to be addressed to the first element of A. If you say BB0, replace this in your mind with a pointer to the first element of the array. We said in the last lecture, you can use a pointer to an array using the indices, right? So if you say, like let's say I call BB0 another pointer, I call it pointer, BTR. Can I write BTR1? I can say this, right? Because BTR is a pointer to array A. A is an array, so you can write A1 or BTR1, right? So this is exactly the same thing. The way it works is BB is an array, BB0 is a pointer, BB0 is pointing to this one, X is the first element of the array that BB0 is pointing to. BB01 is not a memory location. Oh, it's a memory location, right? A1 is an element to that array, which is also a memory location. Oh, you mean not a memory address? This is what you mean. Yes, it's a value of this address. So if you use a pointer using the indices of an array, you are doing dereferencing. This is another way in C of doing array dereferencing, right? If you say B0, you are accessing the element of the array that B is pointing to, right? Of 0 or 1 or 2 or 3. Yeah. If you print, this is a good question as well. If you print BB0, it's going to give you the address here, right? Because here we store an address, right? And you can try these things yourself, right? So you try them, it will give you the address of the first element. Yeah. First, I have 2 minutes. Second, these questions are very important ones, so I guess you don't want to miss. Assume you want to miss and you don't care, at least respect your friend who is asking, right? That's a very good question, right? If you are thinking about access time using this way, you are right. You can like accessing this element because this one too can be in anywhere in memory. It's not contiguous to this array. So it's from this sense that's true. But from another sense, access time is one aspect of a data structure. But also the search is another aspect, right? So what I mean by this is to search an array